So for this section on continuity, in some books it'll be 2.5, in other books it might be 2.6, but just look for the section on continuity. A function is continuous at x equals a if the limit as x approaches a of f of x equals a, okay? I'm sorry, as x approaches a equals f of a. So this little statement right here carries a lot of weight. What it actually implies is these three things must be true. F of a must be defined. The limit as x approaches a of f of x exists and it is a finite number. And the limit as x approaches a of f of x must equal f of a. So basically saying that 1 and 2 must be the same. You must get the same answer from both part 1 and from part 2. Okay, so up here we have a graph. Now the problem with continuity, I feel for a lot of students, is continuity is very, like it seems so obvious. So yes, when we were younger, we were taught, hey, a function is continuous if you can draw it without picking up your pencil. And that's true, but that's not a very mathematical way to explain continuity. So in this section, we're gonna go and rely on a very mathematical approach using limits to explain continuity. So as you can see here, if I look at A, or I shouldn't say equals to, so for point A, that is discontinuous because it's not defined. So f of a is undefined. Okay, now if we look at B, I guess you could say in a way it's undefined, but f of B approaches an infinite level. It is basically creating an asymptote there. So we have the limit of B, let me say the limit as B approaches, or let's say this, as x approaches B of f of x, and let's call this my function f of x. Limit as x approaches B of f of x would be infinity. So it can't be continuous if you can never actually make it to infinity, right? The whole point is it goes on forever and ever and ever. And then for C, well, C, it looks like it's discontinuous at C, but then you can't say that f of C is not defined because f of C is actually defined. It's just not defined in the spot you want. It's actually defined right here, right? It's not defined down here, but it is defined up there. So f of C is defined. However, the graph definitely jumped, okay? So, however, the graph jumps, okay, at C, okay? And then at D, we notice, at D, we notice that if we were going to find the limit as x approaches D of f of x, we would get, let me see, the limit as x approaches D of f of x does not equal what f of D is. And what I mean by that is if we plug in f of D, we're going to get this value right here, right? That's what f of D would become. F of D would be whatever that is. Let's say that's a height of 5. We would say that f of D is 5. But if we were taking the limit, remember I told you guys that you walk on the graph from both sides, the limit would be right here. So let's say that's like 5.5. So the limit and f of D would not be the same value, okay? This limit is approaching infinity. F of C is defined, but not the same, oops, let me write it in black. F of C is defined, but it is not hold on, let me put it this way. But I'll say this better, this is better, but the limit does not exist. Okay, so the limit does not exist even though it is defined. So this is basically showing all three of these situations. So for part A, it would be the first one. So this would be the first one, okay, is broken, right? For part B, this would be the limit exists, but it is not finite. So this would be step 2 is broken, okay? For letter C or point C, this would be where step 3 is broken, right? Because it says that the limit has to be the same as, oh no, for part C, it's not part, it's actually 2 again. For letter C, it's defined, but the limit does not exist, okay? So that's broken. And then for this one, it's step 3, because the limit exists, f of d exists and is defined, but they are not the same number. So part 3 would be broken. So this is how we're going to work with continuity. So in order to show continuity, okay, to show continuity, use the 3, I guess, steps to verify. Now, normally you're allowed to kind of not focus in on places where it's obviously continuous. So for example, I didn't ask you to show me if it's continuous on this interval because it's obviously continuous. So what we do is normally we look for areas where the graph could be discontinuous and we check those. So it's almost like we talk about them as our areas of concern, okay? Here is, I guess you would call this informal. So this would be informal. And this would be formal, and then so on and so on, informal, informal. So this is just kind of a way to talk about it, and then this is the mathematical way to explain it. Okay, so removable, these are types of discontinuities. Removable discontinuities, jumps, or infinite discontinuities. There is a hole in the graph is what a removable is, but that basically means that the limit of f of x is equal to L, but f of a does not equal L. Let me see here, that's one way. Yeah, it could also be, let's see here, the next one is a jump. There is a jump in the graph, and that would be, you know, what we were talking about right here at C. The limit as x approaches a from the right and from the left are not the same number. However, the limits are actual finite numbers. And then there's an infinite discontinuity where part of the graph goes to infinity. Any of the following occur. The limit as x approaches a from the left or the right of f of x is equal to plus or minus infinity, okay? So these are just kind of ways we talk about it. All right, so here's some facts we want to know about left and right hand continuity. A function is continuous from the right at x equals a if the limit as x approaches a from the right of f of x equals f of a. A function is continuous from the left at x equals a if the limit as x approaches a from the left of f of x equals f of a. So a function is continuous on an interval if it is continuous at every number in the interval. So these are just kind of, there's sometimes they talk about left, continuity from the left and continuity from the right, and this is how you can deal with it. I normally focus on continuity as a whole, but these are just some side facts that we can discuss later on. So use the definition of continuity to determine if the following is continuous at x equals 1. So a lot of times with piecewise defined functions, you look at the domain restrictions, and that's normally where you find your areas of concern. So for us, they actually told us to check at x equals 1. They didn't tell us to check anywhere else. So what I'm going to do is I'm going to go through my 3 steps. So step 1 says f of a, okay? So in our case, we're dealing with 1. So is f of 1 defined? Well, if I plug 1 in, that's this guy right here, I'm going to get a 3. So that's a check, so it works. Now I'm going to do step 2. Okay, so step 2 says that I'm supposed to see if the limit exists. Because it's a piecewise function, I'm going to check the limit from the left and the right. So the limit as x approaches 1 from the left of, I'm going to factor this because I'm pretty sure we're going to need to factor it. Because if I plug 1 in right now, I get 0 over 0. So I'm going to use my factoring technique. So this will be x plus 7, x minus 1, all over x minus 1. Okay. So when I take this limit, I can obviously see that the x minus 1's cancel. And I'm going to be left with 1 from the left, 1 plus 7 would be 8, okay? Now I'm going to do the limit as x approaches 1 from the right of x plus 7 times x minus 1 over x minus 1. Now you might be asking, why am I not using 3? Well, think about this. Remember, the whole point of a limit is you don't actually get to make it to that number. So I'm never actually going to make it to 1, right? I'm always to the left or to the right of 1. Well, that's exactly what this is talking about. This is saying When x does not equal 1, you use x squared plus 6x minus 7 over x minus 1. When x does equal 1, you use 3. Well, x won't equal 1 if you're doing limits because you're saying you're approaching 1. You're not saying you actually made it to 1. Okay, so this, once again, I think you guys can see, will be 8. Okay, so that checks out, right? So the limit exists, okay, and it's the same number. So now let's do 3. Okay, so now step 3 says the limit as x approaches 1 of f of x, that equals 8, but that does not equal f of 1. Remember, f of 1 equals 3. So we say the function, so step 3 breaks, right? Or you know what, we could do this. This breaks, this one doesn't work. Okay, no check mark. So we say the function f of x is discontinuous at x equals 1. Okay, so it is discontinuous at x equals 1. All right. So that's how you can do a problem for continuity, and you literally have to go through those 3 steps. The moment one of those 3, I can't draw. The moment one of those 3 break, you're done. You can just instantly say discontinuous at that location. Okay. So in this class, so for this class, you may assume that the following types of functions are continuous on their domains. Okay, so we have, first things first, we know polynomials are always continuous, so you probably would not get a test question that says, is the following polynomial continuous on some interval, because a polynomial is always continuous on an interval. Okay, rational functions. Third one, trig functions. Fourth one, exponential functions. I'm not going to keep writing out functions. Okay, so 5. We have inverse trig functions. 6, we have logarithmic functions. And 7, we have root functions. Okay, so what it means when it says on its entire domain is, so like, let's say you have a rational function. Let's say you have f of x is equal to 3x over x minus 7. Well, this function is continuous everywhere except 7, because 7 is not in the domain, right? So anywhere else on this graph, you can assume that it is continuous except for at 7, but 7's not even in the domain, so we're not checking it. So that's what they mean by these functions are continuous on their domains. Think about it. If you had f of x equals the square root of x, right? Well, we all know that that's this graph right here, right? Well, that graph is continuous on its domain. You're not going to talk to me about the graph over here because the graph doesn't exist over there. That's not on its domain. So root functions, rational functions, exponential functions, when they say they're continuous, we understand there's certain places where the graph doesn't exist or it has discontinuities, but on the domains of these graphs, they are continuous everywhere, okay? So it'll just kind of save you time. Some books actually use these as theorems. I'm just going to say that you can say, hey, the following is a polynomial continuous on its domain. Hey, the following is a trig function continuous on its domain. That way you only need to check the areas of concern. Okay, so let's look at another problem. So let's do something easy. Find the limit as x approaches 3 you know what, let's do this. A few other theorems I want to just briefly write for you guys, okay, is if f of x and g of x are continuous at x equals a, and c is a constant, then the following are also continuous at x equals a. Okay, so we have f of x plus or minus g of x, and basically this is saying a continuous function plus a continuous function is a continuous function. This one is saying that c times f of x, or a continuous function, is continuous. If you multiply it by a constant, it stays continuous. F of x times g of x is a continuous function. So if you take a continuous f of x function and you take a continuous g of x function, and then you try to see if they're continuous at a, if you multiply them, they will stay continuous. So you can multiply two continuous functions and you end up with a continuous function. And then division also works as long as g of x is not equal 0. Or I'm sorry, g of a does not equal 0. Okay, so this is just basically saying that continuity is closed under addition and subtraction and constant multiplication and division. So if you take a continuous function and you multiply it by a continuous function, you still get a continuous function. If you take a continuous function and you add it to a continuous function, the new function will still be a continuous function. That's all they're saying, okay? There's also another one. If g of x is continuous at x equals a, and f of x is continuous at g of a, the composite function f of g of x is continuous at x equals a. So basically, this is saying that the composition of two continuous functions is also continuous. So once again, just, kind of preserving the continuity. As long as the two things you're dealing with are continuous, you're allowed to say that the composition of those two functions is also continuous, okay? All right, so let's try this. Let's say determine where f of x is continuous, okay? So what we're gonna do is this function f of x is a piecewise function, and a lot of times with continuity you will run into piecewise functions because a lot of the other functions it's very obvious they're continuous or not. Piecewise normally require you to do some work, so that's what you should expect to work with in terms of continuity. This is for x is less than or equal to 0. This is the sine of x is, oops, hold on, let me fix that. 0 is less than, x is less than or equal to pi. And then we have e to the 1 over x for x greater than pi, okay? So this is a piecewise defined function, okay? And we want to determine where f of x is continuous, and you must use definition of continuity. So what we went over in class, okay? So when I ask you to prove something is continuous, you must show me these 3 steps. You must show me these 3 things are true, okay? So we come over here. Now what I'm going to do is I'm going to kind of show you guys a little shortcut, okay? So we know that x over x minus 3 is continuous on x less than or equal to 0 since rational function, right? So x over x minus 3 is a rational function. We know that sine of x is continuous on 0 less than x less than or equal to pi since trig function. Okay, and then we know that e to the 1 over x is continuous on x greater than pi, since exponential function. Okay, check, check, check. So each one of these is continuous on their domains. Now, e to the 1 over x would have a discontinuity at 0, right? Because 1 over 0, we probably have some issues there, but this is only talking about when x is greater than pi. This would have a discontinuity when x is 3, but the domain restricts it to be less than 0. So these are all totally fine. However, with a piecewise, even with 3 continuous functions, there still can be some problems we run into with discontinuities. So where are our areas of concern? In general, areas of concern are normally found from piecewise in the domain restrictions. So we're going to look at 0 and pi, okay? So I'm going to come over here, and I'm going to say for x equals 0, okay? I'm going to do step 1. What does step 1 say? Step 1 says that f of 0 has to be defined. So which one of these would use f of 0? That would be this one, right? F of 0 would be x less than or equal to 0. So I'm going to use 0 over 0 minus 3, which is 0. Check. 0 is defined. It is an okay answer. It is a defined number in the real, so we're okay with it. Okay? So now I'm going to do step 2. Step 2 says that the limit as x approaches 0 from the right and the limit as x approaches 0 from the left has to be the same number. So the limit has to exist and it must be finite. So let's see. Which one of these is 0 from the right? That would be this guy, right? Because this is saying that x is a little bit bigger than 0 and smaller than pi. So that would be sine of x. So I'm going to say limit of sine of x, and that's going to be the sine of 0 is 0. And then here we're going to do less than 0 to the left side of 0. So that would be x over x minus 3, x over x minus 3. Now that will be 0 as well, right? Because it'll be 0 over negative 3. So this means the limit as x approaches 0 of f of x equals 0. Check. Okay, so the limit exists and it's finite. And then step 3 says we have to check and see if step 1 and 2 are the same. Well, f of 0 equals 0, which also equals the limit as x approaches 0 of f of x. Check. So it is continuous at x equals 0, okay? Now we're going to do the same thing, but for x equals pi, right? So now we have step 1, f of pi. So we come up here. Which one of these has equals to pi? That's right here, right? Less than or equal to pi. So we're going to say the sine of pi would be what? 0? Okay, check. It's defined. Step 2, we have to find the limit as x approaches pi from the right and the limit as x approaches pi from the left. So we have to see if the limit truly exists. So we're going to come over here, and from the right of pi, that would be this guy, right? Because x is bigger than pi. So we're going to say e to the 1 over x equals e to the 1 over pi. And then this will be from the left of pi. That will be this guy right here again, sine of pi. Sine of x equals sine of pi, which is 0. So that's a problem. Limit is dne. So we're done. We don't even need to do step 3 because step 2 says there is no limit. The limit does not exist. So we're done. Okay. So what I'm going to now say is the graph, or let's say f of x is continuous on the interval. And now let's see here. From 0 it is definitely continuous from negative infinity to 0, right? Yeah, that's going to be continuous there too. Okay, so we can say from negative infinity to 0. Now it doesn't jump or do anything weird at 0, so we can go all the way up until pi. Negative infinity to pi, union pi to infinity, right? Because the only place this graph is discontinuous is at pi. So at 0, it somehow finds a way to connect without being discontinuous, okay? So we don't have to do a separate interval for 0. So negative infinity to pi and from pi to infinity, okay? So that's what the graph is telling us, and we just proved it with our little check, and then I found the intervals where it is continuous, okay? So it says determine where f of x is continuous. It's continuous everywhere except pi, okay? So now let me do the intermediate value theorem, the IVT for short. Okay, so let me write this out, the IVT. Okay, this is the intermediate value theorem. Okay, oops, I'll write it out. I call it the IVT. Okay, so the intermediate value theorem says, suppose, you know what, let me do it like this. Suppose f of x, and by the way, continuity is a big thing in this class. A lot of the theorems we do, they always start out with suppose f of x is continuous. So continuity is a big part of this course, even though it almost seems like redundant or easy to look at something and tell. Proving it mathematically is sometimes harder. So continuity is a big part of what we do. It starts to become a little bit of an afterthought, but you always have to keep in mind that a lot of what we're doing is only legal because it's continuous, okay? So suppose f of x is continuous on a closed interval a to b. Suppose further that f of a does not equal f of b, and let n be any number between f of a and f of b, okay? Then there exists a number c, an element of a, b, such that f of c equals n, okay? By the way, you guys, this is, in calculus, I start trying to incorporate terminology and, you know, the way you might see math written in higher levels. So this symbol here means there exists. This symbol here means element, which basically means in a part of, okay? And then this is how I say, this is how I write such that, oops. Okay, so yeah, I'm going to constantly be doing that. I'm not going to give you a test question where I say, what are these definitions? But a lot of times when I write, I'll try to start writing like this to get you kind of comfortable with how mathematics is written at higher levels. So it says, then there exists a number c, an element of a and b, which means part of a and b, the interval a and b, such that f of c is equal to n. So let's see what this looks like graphically, okay? Okay, now I'm just going to be honest with you. The intermediate value theorem is, this is the intermediate value theorem, but a lot of times what we use it for is to determine roots. We use the intermediate value theorem to find zeros or to find roots of a formula or an equation, okay? So let's say we have this graph like this. Okay, so we're going to stop here and start here, and let's call this A. Okay, and then let's call this, you know what, let's call this A, and let's call this B, okay? And then what we're gonna do is I'm gonna put a few little values right here. Let's say this one, oops, and this one. You know what, that looks bad. Let's do, I think I kind of didn't do it very accurately. Okay, so let's call this C1, let's call this C2, and let's call this C3. Okay, what this is saying is that, oh man, I didn't get it to line up quite right. Sorry about that. What this is saying is that right here, okay, what it's saying is the intermediate value theorem is promising you, it's a promise. It says, suppose f of x is continuous on some interval a to b, and suppose further that f of a does not equal f of b. So they're not the same height. The graph doesn't start off at one height and end at one height. They're two different heights when the graph starts and when it ends. N can be any number between f of a and f of b. There has to exist a number c such that, or part of a and b, such that f of c, when you plug this x value in some c, it will give you the height of n. So that just basically means I could do this. I could do f of c1 and I would get n. I could do f of c2 and I would get n. I would do f of c3 and I would get n. Now again, it doesn't mean there has to be 3 or 4 or 5. There may only be 1. But what it's promising is there is at least 1. Now the thing is, in general, we don't use it to find random heights. We really care about crossing the x-axis because that's a 0. So let's look at a problem that uses it for that. Okay, so it says, prove there is a root of x to the 5th minus 3x to the 4th minus 2x cubed minus x plus 1 equals 0 between 0 and 1. Okay, so first thing we know is, according to the intermediate value theorem, we have to double check a few things. If we want to use the intermediate value theorem to guarantee it, we have to double check a few things. It says f of x has to be continuous. So part 1, f of x is continuous. Now, how do I know? How do I know f of x is continuous? Well, x to the 5th minus 3x to the 4th minus 2x cubed minus x plus 1 is a polynomial. And we know all polynomials are continuous on all intervals, or on any real interval. So f of x is continuous since polynomial. And you can just write that. That's good enough. Okay? Check. Step 2 says that f of a cannot equal f of b. So I'm going to find f of 0, and I'm going to find f of 1. So when I plug 0 in, I get 0 minus 3 times 0 minus 2 times 0 minus 0 plus 1. So I get 1. And then when I plug 1 in, I get 1 minus 3 minus 2 minus 1 plus 1. What is that? Let's see, negative 4, I think. Yep. So then this leads me to know that f of 0 does not equal f of 1. Check, right? So we're good. So step 1 and step 2 are satisfied of the intermediate value theorem, okay? Then what it promises is that there exists a number in between a and b, some number c, in between a and b, right? So somewhere in here, such that f of c is equal to n, some height n, okay? Now, here's the thing. What's the height that we're talking about? Well, our height is from 0 to 1, right? So our interval, I'm sorry, not our heights, our interval, our x values is 0 to 1, okay? So what that means is we want f of c, or we'll say we're looking for f of x equal to 0, since we want f of, since we need to show a root. So remember, in order for something to be a root, it has to cross the x-axis. It's an x-intercept, so that's a 0 of the function, okay? So that means that the n we're looking for is equal to 0, and we can see that negative 4 is less than 0 is less than 1. all right? So this means that therefore, by the way, these are the heights that I got when I plugged in these values. Therefore, by the IVT, there exists a C, an element from 0 to 1, such that f of c has to equal what? What does f of c have to equal? 0. Okay. So what the IVT did is you had to satisfy its first two conditions. F of x is continuous and f of 0, or the two endpoints don't equal the same thing. Now for us, we were looking for n. Okay. You could also say that we also notice that since there is a sign change from -4 to 1, we must cross the x-axis. Therefore, a 0/root must exist on 0 to 1. Okay, that's an alternate way to think about it. This is like a very formal way to talk about it. We're looking for n equals 0. We can see that 0 is in between -4 and 1, our heights. That's just like in the graph. It doesn't work right, but we have this height here and we have this height here, and we're saying that n is, there's got to be some c that can get me to a height in between there. Well, we're looking for 0 because they want a root. So that means because they want a root, which is a height of 0, meaning you're on the x-axis. Well, you went from -4 to 1. What's the only way you could go from -1 to 4 on a graph? You can go from a height. Ooh, whoa, what happened there? The only way you can go from a height of -4 to a height of 1, right, on a graph, is if you're here and you end up here. The only way that could have happened is you had to, now you could have crossed like that. I don't know how many times you could have crossed, but you had to cross the x-axis, which means there is a root. That's all the intermediate value theorem told us, is that it had to cross n equals 0, which means the x-axis, right? It had to cross a height of 0. Now, again, that's important that it's continuous. Otherwise, you could have teleported. You could have just jumped up there. And also the heights weren't the same. So the IVT can only prove the existence of a root. It can't disprove it. So let's say that, the two numbers were both positive on the outcomes. Well, you can't say, well, then there can't be a root, because I could have drawn this. I could have done this, right? Oops. So here, f of a equals f of b. So the intermediate value theorem doesn't apply. So you can't say, well, there's not a root there or something, because as it is, there's actually two roots. So the IVT can only prove existence. It's a one-way street. It can't disprove. Or the other thing is, it can't tell you how many roots. It doesn't tell you that. It only tells you at least one exists, maybe more, but at least one existed. Okay. That's going to do it for this video, guys. In the next video, I'll talk about limits at infinity and horizontal asymptotes. All right, thanks for watching, and see you in class.